Now suppose in a closed system, the gas undergoes the reversible adiabatic expansion process and it follows the law pressure P is equal to 3 plus 4 upon V square, and the unit for this pressure that is given over here is bar. So this is important. We have to convert this bar into kilopascal by multiplying this value by 10 raised to 2, in which the volume changes from 0.1 meter cube to 0.4 meter cube. So volume is changing and this pressure is given by this particular relation, and we have to find out what is the work that is developed during this particular process. So we know that the work done is given by integration of PdV, so it is a PdV work. So apply the limits. So volume is from 0.1 meter cube to 0.4 meter cube. Pressure is given by 3 plus 4 upon V square, but that is in bar. Convert this value in kilopascal. So multiply this by 10 raised to 2 into dV. So take this constant outside. Now integration of 3 dV is 3V. Integration of 1 upon V square is minus 1 upon V. So this value will be minus 4 upon V. And the limits are from 0.1 to 0.4. So in place of V, substitute the upper limit, that is V2, minus the lower limit, that is V1. Similarly, 1 upon V, here also substitute the upper limit, that is 1 upon V2 minus 1 upon V1. And substitute the values. So V1 is 0.1 and V2 is 0.4. So by substituting these values and solving this, we'll get the work done as 30.9 into 10 raised to 2 kilojoule. So consider a steady flow of air through the adiabatic passage. The specific heat at constant pressure of air is given as 1.005 kilojoule per kg Kelvin, and air enters at this particular initial condition. So pressure is 100 kilopascal, temperature is 500 Kelvin, and velocity is 150 meter per second, and it exits the passage at a temperature of 510 Kelvin. And assuming it to be an ideal gas, we have to state which type of the passage it is, whether it is a nozzle or diffuser. So applying the steady flow energy equation, we can say that the enthalpy energy, this is the kinetic energy, this is the potential energy, heat supplied. Then at the exit, this is again the enthalpy energy, this is velocity energy, datum or potential energy, and the work that is obtained. Now as it is a adiabatic passage, there is no heat that is supplied from system to the surrounding or from surrounding to the system. Now there is no work done during the process, so these values we can assume 0. We can assume that there is no datum head that is also present over here, or rather they are same, so we can cancel out over here. So neglecting this datum head, then heat supplied and work done, we'll get the simplified form of this equation, that is H1 plus C1 square by 2 is equal to H2 plus C2 square by 2. So we know that H is equal to mCp into T. So mass is 1 kg, so it is Cp into T1 plus C1 square by 2. Now here the important part is that this enthalpy will be in kilojoule per kg, but this particular value, that is 1/2 m into c square, that is kinetic energy, will be in joule. So we have to convert this value from joule to kilojoule, and therefore we are dividing it by 1000. So this is the most important step that you have to remember. Substitute all these values and you will get the value of velocity as 48.9 meter per second. Now the initial velocity is 150 meter per second and this final velocity is 48.9 meter per second. So as the velocity is decreased, so we can say that it is a diffuser. In case of the nozzle, the velocity will increase for the steady flow process of the air. So in this particular case, the inlet and outlet conditions for the adiabatic steam turbine, they are given. So values of H1, then velocity, datum and pressure, they are given, and at outlet also the corresponding values are given, and we have to find out what would be the power developed in megawatt. So according to the steady flow energy equation, so we can apply this particular steady flow energy equation. Now here we'll convert this kilojoule, in this particular example we'll convert this kilojoule into joule, so multiply by 10 raised to 3. So all these particular terms will have same units, that is along with this kinetic energy, potential energy all these units will have the same unit of what we can say joule per kg. So 3500 into 10 raised to 3. Substitute the value of velocity also. Then datum is 12, G is 9.81, Q is 0. Similarly, substitute the values for H2, C2, Z2 and G over here. So we'll get the value of W. So we'll get the value of W as 1.007 megajoule per kg. Now we know that power developed is nothing but mass flow rate into work done. So mass flow rate is in kg per second. So this kg will get cancelled. We'll get megajoule per second. That is nothing but a megawatt. So power developed is 15 into the mass flow rate. We can calculate the power developed. Mass flow rate is given as 15 and work done in megajoule per kg is 1.007. So answer is 15.11 megawatt.